Thank you very much. So as you were mentioning, I work for Johnson & Johnson. I work in the design of intraocular lenses, and taking the opportunity of Maria, I thought it was a good idea to give you some information of how we create our designs and how we validate the methodology as well. So I thought that one way to do is to just give an example. So because I know this is very general and you have presented a very different topic, maybe this is something that I'm sure you all know, but just in case it's good to refresh what it means to have cataract and what is the solution for that. So we know that with age, the crystalline lens become more dense and start blocking the light so that they degrade significantly the image quality. So cataract is right now the leading cause of preventable blindness globally. So to solve cataract is what we have a intraocular lens. That's what I'm going to be talking today about. So intraocular lenses are this small lens that is implanted inside the eye when the crystalline lens is removed, and it can restore the vision of the patient. There are many different types of IOLs, and I think that's something we can maybe discuss in another time, but there are all different types of intraocular lenses. There are monofocal, there are multifocal lenses, there are lenses that are refractive, diffractive. So there are all different types of lenses to address different needs of the patient. There are patients that want to have a very sharp image for distance and they don't care about wearing glasses, while others prefer to have a small reduction in contrast and maybe visual symptom, but don't need to wear glasses at any distance. So because right now there is nothing that can totally replace the crystalline lens. They are all like a static solution. That's why there is always a trade-off in how much you can improve the range of vision and still keep a high quality distant vision. So that's why there are so many solutions right now in the market, because there is nothing that still replaces the natural lens. So when we design an intraocular lens, there are like 3 levels of information that we can collect. The first one, of course, are the in vitro testing and simulation. We can have an optical bench and we can measure in very determined condition. We can also do in vivo testing, still doing like, for example, visual simulators, where we can look through the optics of the lens or just simulate the performance, have real subject providing their own real, more subjective perspective. And the last part of how we can collect this information is through clinical studies. So in the clinical studies, we have real patient implanted with a real IOL, and then we collected also data from that. So when we design an IOL, we have all these sorts of information, not only to validate that the lens performs as we expect, but also for the design. Because after years of working in this field, we know which in vitro testing predicts very well the clinical data. We know what kind of information we can get in vivo that we cannot collect in vitro. So these are how we design an intraocular lens. So I thought that for today, maybe a good way to present it, how we do it, was to give an example. And I'm selecting the one that I'm more close to, that is the Technis Eichens IOL, because that's the design that I worked from the beginning to the end. So I thought it was a good experience to see how the design was, how we achieved this design and how we validated and the process to get the data. So a Technis Eichens is just now it created the category of enhanced monofocal lenses. So it's a monofocal lens because still your distant vision is as good as it can. You don't have these photopsias or halos, but it's enhanced in the sense that provides a slightly larger range of vision. So you get the patient still need glasses for reading, still need glasses for very close distances, but the intermediate is slightly better. That's the idea of these enhanced monofocal lenses. So Technis Eichens was the first IOL design with that purpose, to be just a little bit better than a monofocal lens. And that means we need to create all a new technology, how we want to evaluate that and how we need to measure it. So how we came to this design, it was we have a purpose. We want to have a monofocal lens that is going to have better intermediate vision. And then when we design an IOL, we have to think what are our design goals. So what do we want to get? We want to have distant vision, like the current monofocal lens, want to have better intermediate vision, want to have a better range of vision as well, want to have the dysphotopsia, so halo, star batch, glare, all the scatter phenomena to be at the level of the monofocal lens.
going to have a pupil-independent performance, and also the risk profile to be as a monofocal IOL. So these are the goals that we have. And of course, there's always trade-off, right? What does it mean to be better? What does it mean to be equal? That's always the trade-off you have to make. So once you have your design goals clearly defined, then we look at different technologies, because how you balance that, it depends on the technology as well. And for eye-hands, we try with all different type of designs. We try with refractive designs. We also try with diffractive lenses. We try, as you can see, with X number of rings, with achroma, without achroma, with spherical aberration, with tonal spherical aberration, with refractive multifocal lenses. We try with all different type of designs, and we check which of these designs could meet all the design goals. So once we have a selected design, we have to check and go one by one if the design meet the design criteria. So the solution that we came at the end is with the Technis eye-hands. It was a design that it was visually indistinguishable from the monofocal IOL. So you can see here the picture. It was a design that was purely refractive, didn't have any rings, and also it was a design that was continuous. So what we did is, instead of having a spherical aberration in the lens or to have a zone with an add power, we created this continuous chaining power. So the power changing continuously in a way that we were able to meet all the design criteria, and we will see later that. So you can see here the power profile. You can see there's more power in the central part, and then smoothly decreases and had the overall asphericity of the monofocal IOL. It was also geometrically, it was the same central thickness. So it was as close as to the monofocal lens as possible, and we just slightly modified the anterior part of the lens. So to validate this design and that it was actually meeting the design goals, we followed two different tracks. So we have the outcome of the clinical study, when we compare of course, the lens with the monofocal lens. And you can see here, these studies are all standardized. So they are prospective, multicenter, bilateral, they are randomized. And we also usually have a follow-up up to 6 months. And we also did with preclinical testing, with optical bench evaluation. So for this one, we developed the metrics to predict the simulated visual acuity, and there's a publication about that. We also look at photic phenomena. We also did computer simulation and realistic eye models. So we used different ways to evaluate the design, and that, I think that's why this example is so good for you to understand how we usually evaluate a design from the preclinical point of view. Because something that is very important when we measure an IOL, is to be sure that we are using, if we want to know how the lens is going to perform clinically, we need to measure in conditions that represent that clinical situation. So if you look at the literature, there are many studies that do, for example, they use the isocornea, that's a perfect lens without a spherical aberration in green light. This is important if you want to understand if the lens is manufactured as intended. But you want to really know how the lens performs in an average eye, then you need to have an average eye. So you need to have a cornea that has a spherical aberration. You need to do the measurement in white light, so you account for not only the spherical aberration, also for chromatic aberration. So all these factors matter. And also you need to have a good metric to predict the outcome that you want to predict. For example, you want to have the defocus curve, as you can see here. Then you need to have a metric that really reproduces that. So for example, we can use like different metrics. That's from a previous publication. We can use the area under the NTF, or the WTF is more like a visual sterile ratio. So you can have more complex metrics than the MTF, that is the standard way to measure image quality in intraocular lenses. So using the correct methods, we can also predict the correct outcome of the lens, or at least to predict in a correct way what is going to be the outcome of the lens. And as I mentioned, this is very important when designing an IOL, because of course, the optical conditions you use are going to determine the outcome that you get. So then what you want to know is how the lens performs clinically. You have to get measurement in clinical condition. So the ISO standards, as it was with the aberration-free cornea in green light, it doesn't tell you how the lens is going to be performing when it's implanted.
So then let's start how we check, how we validate that the lens meet all the design criteria. So the first one was to have the distant vision of a monofocal IOL. So something that is particular for Johnson & Johnson is that all the lenses, they have negative spherical aberration to compensate the spherical aberration of the cornea. So what we have is a standard monofocal lens, as you can see here, has some value of spherical aberration. So we want to keep that correction of the spherical aberration. So when the pupil opens, the lenses still provide very good contrast vision, something that didn't happen, for example, with the spherical lenses, where the spherical aberration is not controlled. So what happened with these lenses, when the pupil opens, especially for mesopic condition, then you have a significant reduction in contrast because the spherical aberration is not controlled. So for the design, we want to keep the same spherical aberration overall for the whole surface of the lens, so we compensate for that of the cornea. And that's what you can see here, that the same spherical aberration for both design when measured in a pupil of 4.5 millimeter. So it's important then to measure the spherical aberration. That's what we expect. And this is the MTF. So this is what we can measure in the optical bench, the image quality we can predict from the optical bench. So the MTF is very goodly correlated with the contrast sensitivity that the patient is going to have. We can measure, like, for example, in 3 millimeter, that tell us the image contrast in photopic light condition, and we can go to a larger pupil size to 5 millimeter to reproduce what happened in mesopic light condition. And as you can see here, what happened is, like, when you have more correction of the spherical aberration, as you can see, then of course the contrast is going to be better when the pupil opens because you compensate the spherical aberration of the cornea. While lenses that don't fully compensate for that spherical aberration or are more neutral, they have that reduction in the contrast of the image. These are the optical bench. If we measure the contrast sensitivity in the real patient implanted with the IOL, we get what we were expecting from the optical bench data, because we see in the optical bench that the MTF is at the level of an aspheric monofocal IOL. That's currently the gold standard in terms of contrast of contrast sensitivity for a patient, and that's what we measure also in the clinical study. So you can see, if we measure in the worst light condition, that's contrast sensitivity in mesopic with a glare source, to create like all of these photopsia that they can create with an IOL. You can see here that they were not different between the new lens, that is the ICB here, and the standard monofocal lens, that is what you can see here. And we tested that for photopic condition, and they were not different. Also for mesopic condition without glare, and again, they were not different. So you can see here, and that's something we have learned as we go, that the MTF was a good predictor of the contrast sensitivity. But also using the more complex metrics that I presented before, that the area under the MTF or the WTF, we can predict also how it's going to be the visual acuity. So in the left, you have here what we predicted. It was the same visual acuity for both designs. And then in the right, you can see what we measure in the clinical study with a very small difference. Of course, the clinical study, you have variability of the patient, but you can see in general, and there are more publications that show that there is a minor difference, almost not different, between the standard monofocal lens and the new design, that in this case called the IB. And same for uncorrected distant vision. The other important point was also the intermediate visual acuity. That was the difference of this design, to have better intermediate than the monofocal lens. And again, using the same metrics, you can see here that we predict an improvement of 1 line in distant corrected intermediate VA, and that's what we measure also in the clinical study. So from our optical bench measurement, using the correct optical condition and the correct metric, we could predict what was going to happen later on in the clinical studies. You can see here distant corrected intermediate VA and also uncorrected intermediate VA. And again, right now, this is the first data that we're collecting with this lens, but now there are many publications that support also this outcome.
Do you have 1 minute left? Sorry.
Oh, okay. I will go quickly. So the range of vision, same story, is the same. Thank you for the note. So the range of vision, the same story. We predicted in the left, we measured in the right, and again, there are many publications that show the same trend, this improvement in range of vision. That's why you get better intermediate. And then Same thing for these photopsias. So for this photopsia, when we measure in the optical band, we see that they were not different in the scatter profile, not different in the halo profile between the standard monofocal lens and the new lens. And actually, when we did look at the clinical data, that's also what we got, because we have an eye model with the correct dimension, the correct cornea, and the correct way to evaluate that scatter. So that's why we were not surprised that at the end in the clinical outcome, that's what we also got. And there is an example of one publication, but there is other publication that show exactly the same trend. And then also we look, of course, is a refractive lens. So you want to see that the pupil is a pupil-independent performance. And this is an example of another way to evaluate the lenses. So for example, we can use realistic eye models and see what happens when you have real corneas. So what happened with the visual acuity, and here you see what happened also for different pupil sizes. So as you can see, the lens is like not different for far and also not different for intermediate. So the lens was actually meeting the design goal that we proposed. And also another important point is the risk profile. Of course, is a monofocal lens, so it's going to be implanted in patients that have any disease in the eye, could be AMD or glaucoma. So you want to be sure that the lens is not going to perform worse than a monofocal lens. And the typical thing that we look in an IOL and are very critical for a new design is, for example, the effect of the decentration. So as you can see here, if the lens is in the center, it's going to be reduced as compared to the monofocal lens. And you can see here a very good vision, even for significant amount of decentration, and also the effect of high order aberration. So what happens, you have a refractive design, you include high order aberration if the image quality is going to be sacrificed or not. And actually you can see here that both for distant vision or also for intermediate vision, even if you have high order aberration in the eye, that doesn't reduce the benefit of the design. So that's basically the process we went when we design an IOL. We need to have a very clear design goals. We need to have also like a very clear, good method that we know that reproduce the clinical performance. And when we do that, we just need to check and then finally have the final validation with the clinical data that the lens meet the design goal that was designed for. That's all I have. I hope I was on time at the end.